Hi, my name's Patrick Harvey.
I'm Jaskeerat Singh. I'm Yesith Singarachchige.
I'm Robbie Feng.
And we've been working on Franken-Bot.
In this presentation, we'll walk through our project poster, showcase a brief demo of the robot operating in both manual and autonomous modes, highlight the features that worked well, discuss the challenges we faced, and explore potential future improvements. We'll wrap up with our final thoughts and conclusions.
We were tasked by our client, Dr. Stephen Knudsen, to repurpose parts from the boneyard in the back of the computer engineering capstone laboratory into a cheap, versatile, and hackable mobile robot capable of navigating an indoor environment such as our lab. To this end, we scavenged a variety of parts, combined them with a few items that we purchased ourselves or borrowed from Dr. Knudsen, and created Franken-Bot. Franken-Bot is capable of both manual operation via a smartphone application, with video from the mounted camera streamed back to the user, as well as limited autonomous operation, in which it automatically navigates and maps its environment to locate pre-trained objects or visual pattern-based tags. In terms of project outcome, Franken-Bot meets the specification requirements, but there are a number of areas for further work. A more capable power supply is necessary to allow untethered autonomous operation. A more robust mapping and search algorithm could improve performance, and of course the robot is designed to be hackable and expandable, so new features of any kind can easily be added.
To connect to the bot, start by selecting the PicoW hotspot and opening the app. Once the app launches, just press connect. This puts you straight into manual mode. The live video feed might take a few seconds to load, so hang tight. Once it's ready, you can control the bot using the joystick, just like this. Up in the top right corner, there's a mode switch menu where you can choose between different autonomous modes like April tag and object tracking. And now we'll see Patrick show off some sick drifts in manual mode. Moving on to a closer look at the bot, you can see its eyes on the LCD display indicating the direction it's currently moving in. Now we switch to object tracking mode. As the robot encounters obstacles, it actively adjusts its path. Here you can see it changing direction again. Eventually, it detects the April tag, smoothly realigns itself, and heads straight toward the target before stopping at a set distance.
Thank you for your attention to our demonstration. We'd now like to discuss the technical aspects of our project in some more detail. What worked, what didn't, and what opportunities exist for future work. From the perspective of hardware and power design, we were successful in making efficient use of our system resources. By utilizing expansion boards, we were able to connect components such as the LCD display, which would normally require a large number of separate GPIO pins using only a single I2C bus. Additionally, we implemented a two-tier design in which a PiPico 2W microcontroller runs all core robot functions, and a more power-hungry Raspberry Pi 5 single-board computer is powered up only when necessary to handle more computationally demanding tasks for autonomous mode navigation, localization, and mapping. This strategy ensured power efficiency. However, within our time and resource constraints, we were unable to power the Raspberry Pi 5 from an onboard power supply, restricting autonomous navigation to tethered operations. Additionally, the boot up time for the Raspberry Pi 5 introduces a significant delay, often in excess of 1 minute, when switching from manual to autonomous operation. On a related note, our two-wheel drive system proved effective and reliable, despite being constructed entirely out of salvaged components, which themselves occasionally proved not to be. Motor variances do cause some degree of drift to one side or the other, especially when operating in autonomous mode, which we could not fully eliminate without a greater degree of sensor integration, but nonetheless the drive system was functional in all respects. Simple eye graphics on our LCD proved quite compelling during demonstrations. However, more thorough use of this display could not be completed due to the time constraints of the project.
Franken-Bot also performs a naive navigation system to move, avoiding obstacles by partitioning the LiDAR 360-degree scan into 4 directional sectors within a 5-degree range corresponding to front, left, right, and back directions, and computes an average distance within each range. When obstacles are detected below a set threshold in any sector, a simple heuristic-based logic determines what direction the robot should move. If the bot is blocked in all 3 sides, it will move backwards. If blocked in front, it will move to the direction with more space, and finally, if blocked on either side, will move to the opposite direction. Robbie is biased to turn right in equal side distant instances. A mover thread sends driver commands to the Pico based on this logic until tracking thread kicks in. A seamless transition between navigation, tracking, and moving the robot is handled through a non-blocking thread handling sequence. The navigate thread, if a tracked object is detected and within a certain proximity, holds the bot. If the object is visible but not close, it engages visual tracking and disables obstacle logic temporarily. Otherwise, SLAM-based exploration and avoidance remains active. The tracking thread works concurrently alongside other threads, LiDAR reader and mover in a non-blocking manner, repeatedly requesting data and catching raised exceptions caused by serial communication issues or serial buffer overflow issues. As an extended functionality, Franken-Bot is also able to simultaneously localize and map its surroundings based on serial input data which relays angle, distance and quality of each point observed in a 360-degree span by the RP LiDAR. A lightweight Python implementation based on Breezy SLAM creates a 2D occupancy grid map where each cell is represented by color pixels with dark for obstacles, white for free space, and gray for unknown spaces. Breezy SLAM uses scan matching technique to estimate robot's position. It compares the current LiDAR scan with the existing map to find the best pose that matches the known environment stored in the occupancy map. Once the map pose is estimated via a new scan, it's overlaid on the existing map, and over time, the repetition of this sequence combines all scans and sends to matplotlib to visualize the map. In SLAM and navigation, we could not implement live transmission of the map to the app due to packet transmission limitations. Also, the generated 2D map is also of less quality due to LiDAR noise interference caused by small indiscernible objects like chair legs and tables. Also, due to sampling rate limits of the RP LiDAR and simplicity of the type of SLAM method we implemented, the map is of less coherence and of less clarity.
Our robot features two modes of visual tracking, April tag tracking and object tracking. As of right now, April tag tracking is completely operational. Once the trained April tag comes into view, it's recognized with high accuracy by the Husky Lens AI camera. At that point, control switches from the LiDAR-based SLAM navigation system to a differential steering system driven by the tag's X coordinate. The robot doesn't pause to align. Instead, it continuously adjusts the speed of its left and right motors to steer toward the tag in real time. As it gets closer, the system monitors the tag's apparent height in the frame, and once the height crosses a predefined threshold, the robot stops, maintaining a consistent and safe distance from the tag. If the tag goes out of frame, control is handed back to the navigation system, which reorients the robot while avoiding obstacles and attempts to reacquire the tag. Object tracking, however, introduces a completely different set of challenges. Unlike April tags, arbitrary objects don't come with built-in patterns or unique IDs. To track an object, the Husky Lens must be trained to recognize it, and for consistent results, the object must be fully within the camera's field of view and meet certain size constraints. It also needs just the right level of visual complexity. Too simple and the camera can't distinguish from its surroundings, too detailed and it becomes difficult to lock on reliably. These nuances make object tracking much less predictable, and therefore more effort is needed towards it.
For the mobile application part of the project, connection and data transmission between app and bot is successful. Controller creates a Wi-Fi access point for mobile phone to connect, and packets are transmitted using TCP protocol between them. Basic control using the app is successfully implemented. With the use of two joysticks, controlling the bot is just like playing a toy car. Video streaming is stable, but frame rate is low partly due to the hardware limitations of the controller and camera, and partially due to the lack of optimization for the program. We initially planned to stream SLAM map as well, but we were running short of time to implement that.
Finally, we'd like to take this opportunity to highlight a few areas on which future work might most productively focus. Firstly, a number of existing features could be refined in order to be more reliable, more functional, or both. Our power system could be redesigned to allow for untethered autonomous operation using a power bank of greater capacity than we could acquire. Our autonomous navigation system could be enhanced to use a more intelligent search strategy, such as frontier exploration. Our chassis design could be refined to more effectively incorporate all elements of the robot. The user interface of our application could be redesigned to be more intuitive and more useful, and we could complete the ability to stream the generated map from the Raspberry Pi 5 single-board computer to the application. And finally, we could replace or at least install a more streamlined OS on the Raspberry Pi 5 SBC to minimize the overhead which currently causes significant delays.
As an easily implementable hackable feature, we propose the integration of a single servo-based gripper that could grip and pick an object based on a visual cue from the Husky lens, which can detect the object or tag, as well as a pan servo which allows the Husky lens to scan in 180-degree angle as well. Also, the display program could be improved to additionally display battery percentage with added mathematical functions to calculate the system power consumption.
In conclusion, Franken-Bot brought together repurposed hardware and custom software into a functional multi-mode robot. It met all the client's core requirements, from autonomous navigation and object tracking to live streaming and manual control. While some challenges remain, the project lays a strong foundation for future development. Thanks for watching.